Types of physical equilibrium. As you know that physical equilibrium only involves the change in the physical states of the substances involved, but the chemical composition remains the same. The physical equilibrium mainly is of 4 types. The first example we can take is of a solid liquid equilibrium. It is the equilibrium in which the solid and the liquid states of the substances are in equilibrium with each other. The example is like water in the form of ice is found to be in equilibrium with its liquid state. Now these equilibriums will always be associated with certain conditions. In this case of in this type of equilibrium, the condition is the melting point. This is what is the condition we have. This kind of equilibrium only takes place whenever we have the melting point of the substance, or whenever we are at the melting point of that substance. So this conversion of ice to water or water to ice always takes place at 273 Kelvin. The second type of equilibrium we can take is liquid vapor equilibrium. As the name suggests, it is the kind of equilibrium in which the liquid and the vapor states of the substances are in equilibrium with each other. Like we can take the example of water in liquid state in equilibrium with its vapor state. This kind of an equilibrium can exist at any temperature, but the condition is that the system should be closed because it is involving the gases, so that the vapors are not escaping out. I can show you with the diagram that if we take water in a beaker, so after some time what we find is that these water vapors escapes into the gaseous state. If we are keeping this vessel open or by beaker open, these molecules will keep on escaping to the space around it. But if we closes it, after some time what we find is that both this water which is present in the form of a gas vapor state and the water which is present in the form of a liquid state will come in equilibrium with each other. The other condition is this kind of an equilibrium is always at a particular temperature. If the temperature is increased or decreased, definitely this equilibrium also is getting changed or shifted. But at any particular instant of a time, this equilibrium which is there between the liquid and its vapors can exist in the closed vessels. The another important thing associated with this kind of equilibrium is the vapor pressure, VP, because these water molecules which are now present in the vapor state will be exerting or will be behaving like a normal gas and will be exerting certain pressure, which we can easily measure by connecting here a normal manometer, a closed end manometer. And the pressure exerted by these water vapors when they are in equilibrium with their liquid state at a particular temperature is called the vapor pressure of that liquid at that particular temperature. I'm repeating again, the pressure exerted by these vapors which are in equilibrium with their liquid state at a particular temperature is called the vapor pressure of that liquid at that particular temperature. As the temperature varies, since the amount of the vapors will vary, the vapor pressure will vary. The physical equilibrium is solid solution equilibrium. It is the equilibrium which is established between a solid substance and its solution or its aqueous solution. We can take the example of NaCl solid, which when dissolved in water and we prepare its saturated solution, then the equilibrium which is established between this NaCl aqueous and this NaCl solid, which is lying at the bottom of the beaker or wherever you are dissolving it, is called solid solution equilibrium. This can be clearly visualized by this example. Like, we have taken a beaker which is having a water and we start adding NaCl to this in small quantities. We keep on dissolving it. Again, when it gets dissolved, we put some more amount of NaCl. It again gets dissolved. Again put some more amount of NaCl. Dissolve it, it gets dissolved. Keep on repeating this till a time comes when you realize that whatever the small quantity of the NaCl you have added is not getting dissolved. It is lying at the bottom of this beaker. At this stage, we say that the solution is saturated. No more solute can be dissolved in this at this particular temperature in which we are preparing this solution. So, in this stage, this solid NaCl, which is lying at the bottom of the beaker, and this NaCl, which is lying actually in the solution in the form of aqueous state, they both will be in equilibrium. It appears that the solid NaCl is not showing any change. That means the state is appearing to be static. But what is practically happening is that this NaCl is getting dissolved and is changing into the aqueous state, and the NaCl which is present in the aqueous state, which is present inside the interstitial spaces of the water molecules, is actually coming out in the form of a solid NaCl. And this kind of dynamic equilibrium is existing between the two. So such kind of equilibrium is called solid solution equilibrium. What is important, or what is the necessary condition for this is that the solution should be saturated. What is saturated solution? The solution in which no more solute can be dissolved at that particular temperature. So such type of equilibrium is solid solution equilibrium. The fourth type of equilibrium is gas solution equilibrium. We can take an example, like we have taken a beaker and we have taken distilled water in it. The purpose of taking distilled water is that it should not have any gases dissolved in it. We take this beaker, keep this in the open air for some time. What we find is some amount of oxygen which was present in the air gets dissolved in this. Now this oxygen which is present and which is actually dissolved now in this water is called aqueous oxygen. And from where this oxygen has come? It has come from the air. After some time, what we find is that these two, the oxygen in the gaseous state and the oxygen in the aqueous state, will establish equilibrium with each other. This equilibrium of a gas with its solution is called gas solution equilibrium. This is again at a particular temperature, and it is represented by oxygen gas, equilibrium, oxygen aqueous. See, this is the same equilibrium which is responsible for the existence of the oxygen in the water, and which supports your all aquatic and marine life, because the oxygen is continuously being dissolved from the normal atmosphere. Now which is actually forcing this oxygen to get dissolved, and this is the atmospheric pressure, which is actually forcing this oxygen to go inside this solution, this water, and therefore this oxygen is getting dissolved. So the equilibrium which is established between a gas and its solution is called gas solution equilibrium. In this gas solution equilibrium, the most important thing to note is this, that the gas, since has no affinity for getting dissolved in the water, will not be getting dissolved on its own. So who is forcing this oxygen to get dissolved in this water is, it is the atmospheric pressure which is forcing this oxygen to get dissolved in it. So that is why, what is the essential thing which is actually associated with this kind of equilibrium is the Henry's law. Which states that the amount of gas dissolved in solution is directly proportional to the pressure of the gas above the solution. This can be represented by M proportional to P, where this M is the amount of the gas dissolved in solution and this P is the pressure of the gas is above the solution. Remember, I am not expressing the units in which this M is represented. It's just the amount, not represented in any particular unit. What we do is, normally in this case is we changes this proportionality like this. Now your amount of the gas which is there in the solution is proportional to your pressure of the gas above the solution, and this P, or proportionality constant, is opened by a constant which is called KH. This KH is called Henry's constant, and we further changes this formula by changing this M into mole fraction. So what is this? Your X here is your mole fraction of gas in solution. So this is what is the exact formula of Henry's law, where the pressure of the gas above the solution is equal to the product of Henry's constant and the mole fraction of the gas in the solution. The unit of this Henry's constant unit will be exactly equal to the unit of your pressure. So if your pressure is in atm, the unit of Henry's constant will also be in the atm. If the pressure is in pascals, your Henry's constants will also be in pascals, because mole fraction has no units. So the KH unit is equal to the unit of pressure. This Henry's constant Henry's law has a lot of applications in different fields. The most important applications of this Henry's law is in your aerated drinks, which we commonly call cold drinks. The CO2 is dissolved in these cold drinks or in aerated drinks under a very high pressure, and the higher is the pressure, more is the solubility. The second application is with the scuba divers. The oxygen cylinders used by the deep sea divers contains helium instead of nitrogen along with the oxygen, because helium has least solubility in blood, and this prevents the bends in the deep sea divers. So these are the two basic applications of your Henry's law, and this is what is the formula of your Henry's law is.